In the summer of 1944, Allied operational planning in Western Europe relied on a logistics system designed to function with near-mechanical precision. Ammunition, rations, vehicles, spare parts, and fuel were scheduled, tracked, and distributed through layered depots and transport corridors. On paper, the system balanced inputs and outputs with measurable tolerances. In practice, one category of supply proved unusually fragile: bulk fuel stored and moved in standardized steel drums. The issue was not a shortage of fuel at the source, nor a failure of transport capacity overall. The failure emerged from accounting and handling assumptions applied to containers that were treated as interchangeable units. Each drum was logged as complete, sealed, and deliverable. Each transfer assumed equivalence between counted units and usable fuel. These assumptions, repeated across ports, railheads, and forward depots, created a cumulative error that was not immediately visible in aggregate reports. As the Allied advance accelerated after the Normandy landings, fuel consumption rose sharply. Armored formations, motorized infantry, and supporting services drew from stocks that appeared sufficient according to ledger totals. Yet frontline units reported interruptions that did not align with recorded reserves. Commanders encountered delays that were difficult to attribute to enemy action or weather. The discrepancy was administrative, embedded in the handling of containers rather than the supply of fuel itself. Steel drums leaked, were damaged, were partially filled, or were lost during repeated handling. Each loss was small. Each miscount appeared negligible. Over time, the system accumulated a deficit that no single report identified. This documentary examines how standardized fuel drums, intended to simplify logistics, became a point of systemic drift. The problem did not result from incompetence or neglect. It arose from a mismatch between design assumptions and operational reality. By tracing records, depot procedures, and transport practices, the episode reveals how a highly organized system can fail without obvious warning, and how administrative precision can mask physical loss until operational effects become unavoidable. Following the establishment of the Normandy beachhead, Allied forces faced the challenge of sustaining a rapidly expanding front. The logistical framework was built around phased supply echelons: ports and beaches feeding inland depots, depots supplying forward dumps, and forward dumps supporting combat units. Fuel occupied a central role within this framework. Vehicles were the backbone of maneuver, and consumption rates increased as distances from the coast grew. The system relied on multiple transport modes, including pipelines, tankers, rail, and road convoys. Where pipelines were incomplete or unavailable, fuel was packaged in drums to provide flexibility. Standard steel drums were selected for their durability and compatibility with handling equipment. They could be stacked, rolled, and loaded by hand or machinery. They allowed fuel to be dispersed across varied terrain and delivered directly to units without specialized infrastructure. The administrative context prioritized speed and continuity. Verification steps that would have required draining, measuring, or resealing drums were impractical at scale. As a result, the system relied on trust in standardized units. Reports aggregated thousands of drums across multiple depots, presenting figures that suggested stability. The context was one in which operational success depended on uninterrupted flow, and where small discrepancies were tolerated as unavoidable friction, not recognized as cumulative risk.
The Allied fuel distribution system was designed with redundancy and simplicity in mind. Standardization reduced complexity across multinational forces. The steel drum became a universal container, enabling compatibility between British and American supply chains. Design specifications defined nominal capacity, sealing methods, and handling procedures. Documentation treated each drum as a complete unit unless explicitly marked otherwise. Inventory systems tracked quantities received, issued, and remaining, with periodic reconciliations at depot level. The design assumed that losses would be statistically insignificant relative to volume moved. It also assumed that damaged containers would be identified and removed from circulation promptly. These assumptions were reasonable in limited operations. In sustained, high-throughput environments, they became vulnerable. The system emphasized throughput over inspection. Personnel were trained to move drums efficiently, not to measure contents. A drum that appeared intact was considered serviceable. Transport documentation reinforced this approach. Manifests recorded counts, not weights or volumes. Transfers between depots often occurred without opening containers. Each handoff preserved the original count, even if physical condition had changed. The design relied on the law of large numbers to smooth discrepancies. It did not include feedback mechanisms capable of detecting gradual volumetric loss distributed across thousands of units. Crucially, the system separated administrative accuracy from physical verification. Ledger balances could be correct while usable fuel declined. The design also dispersed responsibility. No single point owned end-to-end verification from source to consumption. Each node fulfilled its local requirement, assuming upstream integrity. This compartmentalization, effective for speed, reduced visibility of systemic drift. The design worked as intended until operational scale exceeded the tolerance built into its assumptions.
System emerged as drums circulated repeatedly without comprehensive inspection. Minor leaks at seams or bungs released fuel during transport. Evaporation and spillage during handling reduced volume. Drums used as temporary storage were sometimes left open or improperly sealed. Damaged drums were set aside, but records did not always reflect their removal. Replacement drums entered circulation without consistent reconciliation of losses. The failure remained hidden because reporting structures aggregated data. A depot losing a small percentage of volume across thousands of drums still reported the same count. Forward units receiving partially filled drums recorded receipt without measuring contents. Consumption reports indicated higher than expected usage, but the difference was attributed to operational demands or terrain. The drift was distributed, not concentrated, and therefore difficult to isolate. As distances increased, the time between source and use lengthened. Each additional transfer increased exposure to loss. The cumulative effect reduced effective fuel availability without triggering alarms. When shortages became apparent at the front, corrective actions focused on increasing deliveries rather than diagnosing container integrity. This response added throughput but did not address the underlying accounting mismatch. The hidden failure illustrates a classic administrative blind spot. Metrics tracked what was easy to count, not what was essential to measure. The system lacked sensors for degradation. Only when operational consequences became visible did attention turn to container condition and verification practices. By then, the drift had already shaped decisions and constrained tempo.
The operational effect of miscounted fuel drums manifested as intermittent shortages that disrupted planning. Units scheduled movements based on expected deliveries encountered delays. Commanders adjusted routes, postponed advances, or prioritized limited fuel for essential tasks. These adjustments reduced operational flexibility and increased wear on personnel and equipment. Supply officers responded by reallocating stocks, accelerating convoys, and seeking alternative sources. These measures consumed transport capacity and administrative effort. The perception of scarcity influenced behavior, leading units to hoard drums when possible, further distorting distribution. The effect was not a complete breakdown, but a persistent friction that complicated coordination across formations. At higher levels, planners revised estimates and built larger buffers, increasing the logistical footprint. Additional handling increased exposure to the same loss mechanisms, reinforcing the cycle. The operational effect thus extended beyond immediate shortages to influence system design choices mid-campaign. While the Allies maintained overall momentum, the episode demonstrated how administrative assumptions can shape battlefield outcomes indirectly. The impact was measured in hours and days rather than decisive defeats. Yet in high-tempo operations, such intervals mattered. The miscounted drums did not halt the advance, but they constrained it. The system compensated through effort and redundancy, masking the root cause while absorbing its consequences.
Post-operation reviews identified container management as a contributing factor to fuel discrepancies. Records noted losses during handling and transport and recommended improved inspection, sealing, and accounting practices. Emphasis shifted toward volumetric checks at selected nodes and clearer procedures for removing damaged drums from inventory. The lesson was not that standardization was flawed, but that assumptions required periodic validation under scale. The episode reinforced the principle that administrative accuracy must align with physical reality. Counting units is efficient, but only when unit integrity is assured. Where integrity degrades, measurement must adapt. The review also highlighted the importance of feedback loops capable of detecting drift before operational effects emerge. In broader terms, the miscounted drums illustrate how complex systems fail quietly. They do not collapse suddenly. They erode through small, repeated deviations that remain invisible to aggregate metrics. Effective administration requires not only precision but relevance. Metrics must reflect what matters operationally, even when measurement is inconvenient. The Allied logistical system evolved as a result, incorporating lessons that informed post-war practices. The 1944 fuel drum issue stands as a record-based case of how a perfect system, by its own design logic, can generate its own vulnerability. The lesson remains applicable wherever scale, speed, and standardization intersect.